Hello, this is Mr. Huber. In this lesson, we're going to look at direct variation. Two variables, usually we use x and y, vary directly if they can be written in the form like we see here, y equals kx. Okay? Where k is some non-zero number. If k was 0, it would be y equals 0 times x, which would just be 0, so it wouldn't give us anything. And that k value is called the constant of variation. It tells how y and x vary with each other, and that constant in any particular problem is going to stay the same. It might be y equals 5x or y equals 1/2 x. Okay, but in any particular variation between y and x, if they're direct, we're going to have a constant of variation that we can use to relate them. Let's see if we can figure out whether these two variables vary directly, the x and the y here. In number one, what we want to do is see what this equation will look like when we solve it for y. So if we add x to both sides, we'll end up with y equals x plus 1. This does not look like the form we have right up here. All right, we do not have just a y equals kx. We have this plus 1 on the end there. So that shows this is not constant variation. Okay, it's not direct variation, excuse me, because there is no constant of variation. Okay, not direct variation. In the second example, if we want to solve this for y, we can subtract 2x on both sides, and we get y equals negative 2x. There's our function rule. It says the function rule, this is the function rule. It's the equation we can give that relates these two variables as a function, right? We saw functions before. We could write that as f of x equals negative 2x if we wanted to. Okay, variable we use here is y, so there's a function rule y equals negative 2x, and the constant of variation is negative 2. Okay. In the third example, we want to solve for y. We can subtract 7x on both sides, so we'll end up with negative 5y equals negative 4x. Divide by negative 5, and we'll get y equals 4 over 5x. Negative 4 over negative 5 is a positive then fraction, and the constant of variation is 4 over 5. So there's our function rule and our constant of variation. Again, if we can get an equation that's written as y equals any constant value, a k value, times x, then we have a direct variation. Another thing that's important about direct variations is that constant of variation is the ratio of y over x. Right, if we take our equation that we have, we normally right here, y equals kx. If we divide both sides of the equation by x, it will cancel out here, and then we'll have y over x on the left side. So that constant of variation is always going to be equal to the y value over its paired x value. Okay? So we can use that relationship to figure out our constant of variation in various situations. We'll see a few of them here. In numbers 4 and 5, we want to figure out if y varies directly with x. We don't have an equation necessarily to say y equals kx and see what the equation looks like, but we can see if there is a constant of variation. If you recall, the constant of variation is y over x. So in the first ordered pair, 10 and 5, we'd have 5 over 10, which is 1/2. Here we'd have 1 over 2, which is 1/2. Y over x, 6 over 12, which is 1/2. And then for the last ordered pair, we'd have 10 over 20, which is 1/2. So there is a constant of variation of 1/2. Constant of variation is 1/2, and the function rule would be y equals 1/2 x. So we've determined there's a constant of variation because every y over x comes out constant, the same value, 1/2 in this case. And we can write our rule with that, and we know what our constant of variation is. In number 5, if we put the y value over the x value in all of these instances, we're going to find that most of them come out the same. 15 over 3, that's 5. 20 over 4, 5. 50 over 10 is 5. 30 over 7 is not 5. 35 over 7 would be 5. So this is not a constant of variation. Okay, this particular y over x doesn't return the same k value y over x as the rest of our paired numbers. So this is not a direct variation. We wouldn't be able to write a function rule, find a constant of variation. It's got to be the same constant of variation for the entire set of information, not just some of it or part of it or most of it, but all of it. Another couple ways that these can be presented where we want to find that constant of variation. Okay. Number 6 talks about the graph. We don't even have to see a graph here. If we know it goes through the point 4, 6, right, that's an x and a y value. So right here we have an x and a y value. Okay. We want to write the direct variation equation using those so we can find our constant of variation. The constant of variation is y over x. Right? The constant of variation is always the y over the x. We can reduce that then to 3 over 2, and we can write y equals 3 over 2x. That's our function rule. Then our second part says to find the value in x equals 24. So we can write y equals 3 over 2 times 24. We can put that 24 in for x. We can substitute it in for the x in our equation. And if you remember, this would be like 24 over 1. And so we could reduce that to 1 and 12. And so now when we multiply, 3 times 12 will get 36. So when x is 24, y is 36. We'd end up with an ordered pair, 24, 36. In the next example, we're given an x and a y value. It's not as an ordered pair, but it's saying y equals 6 when x equals 20. If we wanted to write that as an ordered pair, it would look like 20, 6. And now it's identical to what we just did. We can write our constant of variation as y over x. And if we reduce these, that'd be 3 over 10. And so then we could write y equals 3 over 10x. And we could plug in for x 28. And we could put that over 1. And then when we reduce those to multiply, we'll have 5 and 14. We can do 3 times 14 is 42 over 5. So that'd be 8 2/5, 8.4, depending if we want to give a decimal. And we could get a y value in x is 28 by doing it the same way we did the problem before. Or there's another way we could organize this. Say we're going to show a different way that we can organize this same problem. Okay? Instead of writing out the k value, we can know that the constant of variation, okay, is y over x. That's going to be constant for every y and x value. So when we know that y is 6 when x is 20, that should be equal to some y value when x is 28. And we could reduce this before we cross multiply, or we could just cross multiply the way it is. Since we've got calculators to use, that might help us out. Okay, but if we wanted to reduce it, again, that'd be 3 and 10. And then if we cross multiply, we'd have 3 times 28 and 10 times y, so we'd have 10y equals 84. Divide both sides by 10, and you get y equals 8.4. I'm typically going to, if I do this problem, write it this way. Write a proportion. Y over x equals y over x, and then cross multiply. But you can see we'd get the same answer. I'm not going to say you have to do it one way or the other, but it's good to know different strategies. The biggest thing here to remember is that k is equal to y over x. K is always equal to the y value over the paired x value. Right? Let's take a brief break for some alliteration. What is alliteration? It's an English language arts term. Brief break is an example. Right here, brief break. That's an example. Both words start with the same sound. Brief break. There's lots of alliteration in the world. It's used oftentimes, like Best Buy, Ford Focus. So, what I'd like you to do is think of some examples of alliteration. If you email me one before school tomorrow, then I'll be able to give you some extra credit points. If you can give me an example of alliteration in the real world, other than the two I gave you, come up with a couple of your own and see what you can find that's out there. There's so many. Now let's look at the graphs of direct variations. Okay, graphs of direct variations are always going to be straight lines that go through the origin. They're always going to go through the point 0, 0. Remember, if y is equal to kx, then if x is 0, y is going to be k times 0, y is going to be 0. So when x is 0, y is always going to be 0. That's why direct variation will always go through the origin. Okay? So now let's look at how we can use that to our advantage. So we've got a equation here, y equals 2x. So we know the graph's going to go through this point right here. If we make a table of values, right, we could say when x is 1, y is 2 times 1, which is 2. Okay, so when x is 1, y is 2. We could draw a line through those points. You could get a couple more if you want to make sure your points are in the right spot, you didn't make a mistake somewhere. Okay, you get 2 or 3 or 4 points. The more you get, the more accurate your graph's going to be. I'm going to pick a negative number. Let's say negative 3 for x. That'd be a negative 6 for y. 2 times negative 3. So we go negative 1, 2, 3 for x. 1, 2, 3, 4, 5, 6. Negative 6 for y. We'd have a point right about there. And again, if we draw our line through those points, that's our direct variation graph going through, again, the origin. The origin right there, right? That point right in the middle where the x and y axis meet. If you want to graph the next direct variation, and we can pick some values to plug in, we know that it's going to go through the origin. So right there, we know we're going to have the point 0, 0. In this case, what numbers you pick for x and y can make the work a little easier. If you pick 1, you're going to have negative 3/4 times 1. That could be, tricky to graph possibly, but if we plug in a 4 for x, now we have negative 3/4 times 4, which is 4 over 1. Those cancel, we'll get negative 3 for the y. So when x is 1, 2, 3, 4, y is 1, 2, 3, negative 3. Again, you could get more points if you wanted as well. We can draw our graph through those, extend our line, put an arrow on the end. One thing you should notice from these graphs, when you have a positive value for k, okay, when you have a positive value here, your graph's going to go up to the right. When you have a negative value for your constant variation, your graph is going to go down as you move from left to right. So that's something to keep in mind. Okay? How do the graphs differ when a is greater than 0, or k value, that number in front of x? When the k value, we'll change that here to k, is greater than 0, right, you have a graph going up to the right. When k is less than 0, you'll have a graph going down to the right. So keep that in mind. That can help when you're graphing, or if you want to see if your graph looks like it's on the right track, you can make sure that your graph's headed in the right direction based on what that k value is, positive or negative. Now let's look at a real-world type example. Okay? We're talking about how much salt water we need, sea salt we need in the water for our fish tank. Right? Some fish need salt water. So in this particular example, we know that the pet shop is recommending 100 tablespoons of salt for every 20-gallon tank. Right? So we want to write a direct variation equation for this. So using S and W for the amount of sea salt to the number of gallons of W water, we will know that S equals KW. We want to find out what that K value is, so that's going to be S over W, right? Instead of Y and X, we have an S and a W, that's okay. So 100 tablespoons of sea salt for every 20 gallons in the tank, that's our K value. So our equation would be S equals 5W. 100 over 20 is 5. So S equals 5W. And this is how many tablespoons of salt should be added to a 30-gallon saltwater fish tank. So S equals 5 times 30. Right? The 30 gallons, that's our W. W is the number of gallons of water. So we can take the 30 and plug it in for W, and we would need 150 tablespoons of salt for that particular size tank. Remember, we could also write this out as 100 over 20 equals S over 30. So we could do 100 over 20 equals S over 30. You could even reduce the 100 over 20 if you want to. You don't have to. With the calculator, you can cross multiply those numbers relatively easily as well. Okay, so we can cross multiply here, and we get 3,000 equals 20s. Then divide by 20 on both sides, and 3,000 divided by 20, you'll still get the 150 tablespoons. So again, a couple different ways we can write that out. One of the biggest keys there is to know that constant of variation is always going to be y over x, or in this case it's s and w, and we can use that to find a constant of variation, write an equation, set it up as a proportion, and be able to work with those direct variations between those variables.